All right, ladies and gentlemen, wonderful humans, this is going to be your introduction to drawing ionic and naming ionic compounds. All right, so you do need to be following along with this on your weekly sheet. All right, underneath the Monday/Wednesday ionic compounds. All right, so this will not go step by step through all of it. You will have to infer some of the information, but you will have the basics to be able to answer every question. All right, so diving in, we should be familiar with this, but what is an ionic compound? All right, so you should have watched an introductory video yesterday or today with looking at what are ionic and what are covalent compounds, okay? So ionic and covalent compounds both have a place in chemistry, all right? The difference between them is going to be the types of bonds they form and the types of elements that are going to form those bonds. So we start by looking at our periodic table, all right? And I've divided it on our stair step, showing our metals to the left and our nonmetals to the right, with our metalloids surrounding that stair step. And that those metalloids can share properties with nonmetals and metals as well. Actually, a lot of these are the reason that we can have technology with semiconductors. All right. So in blue is our metals. In pink is our nonmetals. All right. And an ionic bond is between a metal and a nonmetal. All right. And in an anionic bond, which is why it's different, two reasons it's different than a covalent bond. It's between a metal and a nonmetal, and electrons are either fully gained or lost, okay, forming ions, okay? That's why it's called an ionic bond. The word ion is literally in it, okay? So in ionic bonds, elements, metals and nonmetals, are going to form bonds by forming ions, but either gaining or losing electrons, okay? And we know when you gain or lose an electron, you're going to form ions. Ions can be positive, which are cations, and then they can be negative, which are anions, all right? Remember, cations have pause, they are positive, and anions are negative ions, okay? So they're all going to form cations and anions from that exchange of electrons, all right? And the amount of electrons that's going to be gained or lost all depends upon, again, back to that golden rule of chemistry, which they're trying to obtain a full octet. So it's going to be based off the octet rule, all right? The amount of electrons that are gained or lost by your cations and your anions. You should be familiar with the amount of valence electrons each element has and the type of ion that they should form, all right? If you're still struggling with that, please reach out to your teacher. That's one of the roots that's going to make it really, really easy for you to be able to do all parts of this unit. So if you are still struggling with the number of valence electrons for each individual element on the periodic table, or will they gain or lose, please reach out to your teachers, all right? So there is an exception to this, which are the transition metals, all right? Those beautiful little elements in our D block, okay? And they're going to vary in the number that can be gained or lost for electrons. They're actually only going to be losing since they are metals, okay? And that's going to be shown by Roman numerals within the formulas, within the naming. My apologies. Within the naming, and that's going to be discussed later on in the unit and is going to be shown by these Roman numerals in the names themselves, okay? But there are the exception. Otherwise, you're going to be able to tell the amount gained or lost specifically by the octet rule. All right. Moving forward, all right, we're going to do some examples here. We're going to look at how we draw ionic compounds and how we write ionic compound formulas. We're also going to be looking at a simple way to check how many elements there are going to be in each, and then we'll finally end with naming. All right, so our first example that we're going to be doing here is going to be doing a drawing for aluminum and oxygen, okay? So the main thing that you need to keep in mind, whether you're using the total calculation of charge or you're doing the drawing, okay, they're all aiming for that octet rule, and overall our charge has to equal 0, okay? So the total charge, the sum of the charges, has to equal 0, okay? And all elements involved either have to completely lose all of their valence electrons or gain their valence electrons, okay, to reach that magical number of 8. All right, so we're going to start with the drawing portion. So we're looking at aluminum and oxygen. So the first thing that you're going to do is you're going to draw the Lewis dot structures for both of the elements involved, okay? So aluminum has 3 valence electrons. Oxygen has 6, okay? So when you do a drawing of ionic compound, you show the movement of electrons. So either the losing of the electrons or the gaining of the electrons. So aluminum needs to lose 3, oxygen needs to gain 2. All right, so we first can show that aluminum is going to give 2 electrons to oxygen, all right? And that oxygen is set. It has all 8. It's very, very happy. The issue that we run into, though, is that aluminum still has 1 more valence electron to lose, okay? And it has to lose that valence electron. If anything, we've made it less stable right now because not only has 1 valence electron left, okay? We're all trying to reach that octet rule, all trying to become stable, okay? So the way that they're able to balance out these compounds is either by adding more aluminums or adding more oxygens, okay? So remember that there's not just a single, when you look at aluminum and oxygen, there's very rarely ever going to just be a single atom of aluminum and a single atom of oxygen, okay? Remember, atoms are super, super small. So there's going to be a plethora of them in that area, okay? So they're able to adjust to find the correct ratio of how many aluminums we need and how many oxygens we need to have a total charge of 0 and have everyone obey the octet rule. So since my aluminum's the one that needs to lose another electron, I'm not going to add another aluminum because that would just increase my problem. I'm going to add another oxygen. All right, so when I add another oxygen, that aluminum's able to lose its last electron, making it stable, but we made more trouble. This oxygen still needs 1 more valence electron, okay? So you're going to go back and forth. So, nope. We're going to go back and forth. Sorry, guys. Going to go back and forth, adding and subtracting aluminums and oxygens till you have the correct ratio. So since that aluminum is now correct, we're going to add another aluminum to balance out that oxygen. All right, that oxygen's happy, but that aluminum still has 2 more. All right, so we add another oxygen. Gosh, I gotta stop hitting that button. Sorry, guys. You add another oxygen, okay, and then that final aluminum gets rid of both of its valence electrons, and that final oxygen has a full 8, okay? So this is showing the movement of electrons that actually occurs within the bonds, all right? But our final product of an ionic bond is not just the drawing with the movement of the electrons. They're going to form ions. So we show the final ions that aluminum and oxygen are going to form, okay? And it is important to make sure that you show all of the elements that are involved because, again, we have to have that net charge equal to 0, okay? So we have 3 aluminums for every, oh my goodness. We have 2 aluminums for every 3 oxygens, okay? Another way that you could write this is with brackets to make your life a little easier so that you don't have to draw them all out. The 2 goes in front, bracket, aluminum, a +3 charge, and then 3 oxygens with a -2 charge, okay? So again, the drawing of ionic bonds are to show that movement of electrons. It's to show the ions that are going to form. It's to make sure that each of those elements are obeying the octet rule, all right? Another way that we can see how many of each element we're going to need is to do the calculation of the total charge. As I mentioned before, that total charge has to equal 0. So a way that you could calculate how many you need is to write out the charges and do the math, okay? So if we look at the final products, aluminum is going to be +3, oxygen is going to be -2. If we summed up their total charges as it is written 1-to-1 ratio, okay, they'd have a +1, all right? So then we would know that we need to add another oxygen to balance it out because we need our charges to equal 0, okay? So we add another oxygen, and that's going to change the charge, okay, to equal, we got a +3, -4, oh, we're still not balanced, okay? So now we're negative, so we're going to add a positive, so we add another aluminum to +3, which means that we have 6 -4, which is +2, we add another negative to equal -2, okay? So as you can tell, both methods have a place, okay? So if you just need to figure out quickly what the ratio is going to be, you can use the calculation of total charge. If you need to show the formation of the ions, if you need to show the movement of those electrons, if we ask you to draw out, you're going to have to be able to draw out the movement of the electrons and the formation of ions, okay? The nice thing is that both methods will be able to show you how to write the formula, okay? So the formula just simply shows the amount of each element with a subscript, okay? So we're not showing the charges, we're showing the amounts in the ratio. So this is literally showing the ratio. So in this ratio, we know that we have 2 aluminums for every 3 oxygens, okay? And that's the purpose of the ratio, is to just simply show how many aluminums you'll need for how many oxygens, all right? So we're going to do one more example with this, looking at the bond between magnesium and chlorine, okay? So for this one first, I'm going to do my calculations of total charge, just in a reverse. So I write out what I have. I have magnesium's going to form a positive 2 ion, chlorine's going to form a negative 1 anion. So if I did my calculations right off the bat, plus 2 minus 1, I'm going to have a positive 1, meaning that I'm going to have to add another electron, okay, another negative anion in the form of chlorine, all right? When I have another negative, it's a positive 2 minus 2, oh my goodness, sorry guys, a positive 2 minus 2, all right, which means that we're going to get a negative 2, and an overall charge of 0, which is the overall goal of our ratios, okay? So this one's a slightly easier calculation where only 1 magnesium is needed for every 2 chlorines to get that ratio, okay? And we can go ahead and write the formula off of that. All right, 1 magnesium for every 2 chlorines, all right? In formula writing, we do not write the number 1, okay? I always say it's because chemists are super lazy, but you're never going to show the number 1. It's just an assumption that if there isn't a number, that's 1. So 1 magnesium for every 2 chlorines, okay? We can also go ahead and draw out the formula. So when we're drawing it out, again, guys, we start with the Lewis dot structures, okay? Magnesium starts with 2 valence electrons. Chlorine starts with 7, all right? Magnesium's going to donate 1 of its valence electrons to the chlorine, making that chlorine stable. All right, but magnesium still has 1 more to lose, meaning that we need to add another chlorine, okay? That magnesium is going to give up its final valence electron, meaning that chlorine, all elements involved, that chlorine is now balanced and that magnesium is now balanced. Okay, but that's not our final product. It is an ionic bond. It must end in ions, okay? So we go ahead and draw the magnesium plus 2 and then the chlorine, both of them minus 1, all right? And of course, you can write this in brackets to make life a little bit easier if you so choose. I'm a big fan of the brackets. All right, and again, you could also find out the formula from this drawing as well. So both methods allow you to write the formulas, but also they have their specific purpose. So if you're trying to quickly find the ratio, obviously the charge calculation is going to be easier, whereas drawing does the actually demonstrates the movement of electrons that's really occurring when ions are formed, okay? So the final thing that we need to look at is naming ionic compounds, all right? So naming ionic compounds is probably, it is a little bit easier than covalent compounds, as you guys will see, till we get into like polyatomics and things like that. So the very nice thing is the first thing that you're always going to name is the metal, all right? And the metal doesn't change. We will have eventually the addition of Roman numerals, but lucky for us, neither of these are transition metals. Makes our life super easy, okay? So we just name them as is, all right? So aluminum is just aluminum, and then magnesium is just magnesium, okay? So there's no change to prefix or suffix, okay? The addition of Roman numerals would come after the official metal name. All right, now our non-metals, okay, we do change the suffix, okay? So for example, for oxygen, we get rid of the YGEN, all right? Normally you get rid of the last 3 letters, but because oxygen has that Y, you get rid of all of it, okay? And the suffix we always add is an IDE. So oxygen turns into oxide, all right? So chlorine, all right, we remove those last 3 letters. There's not a vowel before the last 3. So we just remove 3. Chlorine becomes chloride, okay? So that's the basic rudimentary of naming ionic compounds, all right? So you end up with aluminum oxide and magnesium chloride, okay? Again, metal goes first, all right? Always goes first. You never, ever, ever write the non-metal first. It's always metal, then non-metal, okay? And that metal's name does not change, but that non-metal does get the suffix of IDE. All right, so after this, there are some practice problems for you guys to try. So just do your best and see how you're doing with ionic compounds first.